Alright, this is a continuation of the last video. Ran out of space on the memory card, so I had to switch that out. So, at the very end of the last video, I introduced this integral. You haven't seen this before. These are just two signals. We're saying a signal x of t and a signal y of t that are complex conjugate. If you take the integral over these, it's very, very, very similar to a dot product that is... So what I'm trying to do is relate this to something in mathematics that you're used to seeing. So if we consider this where we have an integral of two signals and one is the complex conjugate of another, and it's very similar to the dot product, let's look at how that would be applied if we're doing a Fourier series analysis. So consider this integral. Consider two sinusoids. If we have so consider two signals. So if we have 1 over t naught, the integral from negative t naught divided by 2 over to t naught over 2. This is very similar to the start of the Fourier series integral. And let's say that this first x of t, the x of t, is e to the j omega naught kt. So just some random signal that happens to be very similar to something that we're solving out towards. And we have another signal. And let's say that it's the complex conjugate of some y of t. So we've got e to the negative j omega naught m of t. So something just a little bit different. Okay, so these are complex conjugates of each other. So they show like that. And this is going to be equal to now 1 over t naught, the integral from negative t naught divided by 2 over t naught over 2 to e to the j omega naught k minus m of t dt. Alright, so let's look at this for just a second. What I'm saying, this is a complex sinusoid. This, with m and k, is a different complex sinusoid. I'm missing a dt. Everything in the Fourier world is a combination of sinusoids. So if we're looking at these two sinusoids and we're multiplying them together, and we know that one is a complex conjugate of the other, what that does for us in the resulting integral is it gives us this same, if they're the same omega naught, k minus m. So it's like a dot product if they are going in the same direction. These things will get bigger. However, if these things are going in 90 degrees offset, this will all cancel out. So in this example that we wrote up on the board, we can see that these guys are of the same fundamental frequency, and then they have this k and this m. The k and the m, depending on what values they are, this is where we get that dot product like behavior, where if they're the correct values, so these are going in the same direction, meaning that the fundamental frequencies, if we put this on a graph, if these fundamental frequencies are occurring at the same point, so let's say that that is x, and let's say that the other one is going here. Those are supposed to be on top of each other. I drew them to the side so you could see some differentiation between them. If these are going together, they're going to sum up. They're going to get a lot bigger. And if they are the inverse, and this is all dependent on what these k and m values are. This is going like this. These are going to negate each other out. So a lot can be done just looking at the exponential of these to figure out if it's going to build up to something bigger or if it's going to destroy and zero out given the harmonics. So what we're looking for is how do these harmonics interact. Alright. I'm going to stop this video and clean up just a minute.